Hi everyone, thank you for being here today. I'm Shichen Zhan from the SKL LTIC at the University of Macau. Today, I'm excited to present AssyLLM, our framework for efficient federated fine-tuning of large language models. Let's dive in. Let's start with a common scenario. Fine-tuning large language models with domain-specific data is a great way to boost performance. But in practice, this data often lives on edge devices like phones, sensors, or IoT systems. Centralizing it can raise serious privacy concerns, and in some cases, even violate regulations like GDPR. Okay, federated learning offers a promising answer. Instead of moving the data, each device fine-tunes a copy of the model locally and only send updates to a central server. These updates are then aggregated to improve a global model. That way, we preserve privacy and make use of distributed data. This idea has inspired a wave of work on federated learning for large language models. We call it FedLLM. But the memory war is a big challenge. Fine-tuning something like Llama 7 billion can take over 40 gigabytes of memory. Most edge devices cannot handle. Even parameter-efficient fine-tuning methods like LoRa or adapter-based tuning still require maybe more than 15 gigabytes. It is still too heavy for most edge devices. This means many devices simply cannot participate, which limits data diversity and hurts the model performance. From Figure 1, the Oracle is the ideal case where fine-tuning happens without any memory constraints. On the other hand, the practical refers to the realistic scenario where memory is limited, just like on most edge devices. From Figure 1, we can see the memory limitations have a huge impact on participation and accuracy. Take Llama 7 billion, for example, fine-tuning them requires over 45 gigabytes of memory. Because of this, around maybe 70% of clients cannot join the fine-tuning for Llama. This significantly reduced the data diversity and led to much worse performance. We are talking up to 14% accuracy drop for Llama model. Okay, then let's take a quick look at the current memory saving methods and why they are not enough. First, the PFT, like LoRa, QLoRa, and adapters, they shrink model size or fine-tuning incomplete large language models, but often at the cost of accuracy. In other ways, the BP-free method, they avoid the backpropagation, but they tend to be unstable and difficult to train. Take LoRa from the figure, take QLoRa as an example. It cuts memory and speeds things up, but still drops accuracy by over 5% in constrained settings. Other baselines suffer the similar trade-off. And then the system-level method like recomputation and swiping, they also help reduce memory. Recomputation discards the intermediate activations and recalculates them during the backpropagation. And for the swiping, they offload part of the model to storage. All these methods can achieve near Oracle accuracy, but the cost is massive slowdown. From the figure, we can see fine-tuning from, say, for example, the fine-tuning time just jumps from nine to nearly 28 hours, and training becomes much less efficient under tighter memory constraints. In a word, the current works successfully reduce the memory overhead, but they sacrifice the performance or efficiency. Then we can get a conclusion. A new fine-tuning paradigm guaranteeing performance and efficiency is urgently required in real-world cases. And here is the big idea behind AssyLLM. Instead of instead of single model, we utilize multiple pre-trained models for better generalization ability. And instead of training, we generated global models by just splitting and assembling. Okay, let's walk through how AssyLLM works step by step. And from this figure, the first step, we start with initialization. We take several pre-trained large language models and then we split them into smaller blocks. And then we forming a block pool. The second, on each client, we perform the local block selection because the clients try different combinations by assembling candidate blocks with the current model structure. Then they run the inference computation on their local data to see how well each combination performs. And based on these results, they calculate a compatibility score for each block and pick the top ones. Third, the client simply uploads their selected blocks, or more specifically, uh, just the index or the scores of these blocks to the server. And this step is lightweight and avoids sending large language model updates. In the last step, the server aggregates the selected blocks using a weighted voting chain based on the compatibility scores. The most compatibility scores are then stacked together to form a new candidate model for the next round. This circle repeats until a complete model is assembled or we hit the maximum model depth. And this is the whole process of our assembling model generation. And SCRM is built on two core ideas. The first is that the pre-trained LLMs already holds rich knowledge. We just treat each block as a reusable intelligence. The second, instead of full model fine-tuning, we selectively assemble relevant blocks for each task. And another important benefit is that the SCMM requires only forward paths. This is a big idea because this is a big deal because in traditional fine-tuning, most of the memory is actually consumed by storing activations for backpropagation. So by skipping backpropagation entirely, we eliminate the need to store these intermediate activations, which result in significant savings in both computation and memory. This makes our approach much more suitable for the resource-limited edge devices. Of course, this assembling approach introduces three big challenges. The first is how do we know if two blocks are compatible? Second, how do we assemble blocks from different models? Some may differ in size, structure, or semantics. And the last challenge, what about the memory? Because a big block pool could quickly overflow the edge devices. And to tackle these challenges, we introduced SALM and Federated Learning system for deploying large language models that optimize memory and performance. Let's look at how we solve this one by one. The first, the block compatibility. Because the more compatibility between a candidate block and the model, the higher the performance of the generated assemble model. However, blocks show structure and feature difference. From figure 9, we can see the different model, even with the same input, they can produce very different features. So measuring the compatibility is a key to assembling effective models. And to measure the compatibility, we use two things. The first matrix is the centered kernel element we call CKA, which compares the output activations. And the second is the layer correlation we call COR for shorts. The which the COR looks deeper in intermediate difference using the Kullback-Leibler divergence. And we use these two metrics for compute the compatibility. And why do we need these two metrics? Because the CK alone is not enough. It will always misses the layer-wise mismatches. And so the COR will fill the gap between the layer by layer. And from figure 10, we can show why this matters. Uh, while the high from the first figure, subfigure, we can see the high CK and the high COR, they will get a great performance like the block one. But in other ways, the high CK but a low COR will not good enough like block two. The accuracy is lower than the block one. And for also for the high COR but low CK, they still weak, like block 4. So as a result, we need both for reliable block selection. By weighted combining both, we just get a much more accurate measure of how well blocks work together. The block compatibility. It helps us to select the best fits, like block 1 in this figure. Okay, next. How do we connect these blocks? This is the second challenge. This is the second challenge. Because even if the different blocks are compatible, but mismatches can happen. So we solve this with elastic adapter, a lightweight model that adapts mismatches blocks. And different blocks from different large language models, they always have three types of mismatch. They are dimensions, they could be dimension misalignments. And in this case, we fix it with linear projection. And they could be semantic inconsistency. And we solve it with, we use cross-attention alignments. And maybe they also maybe the attention mechanism difference, and then we just reshape them as needed. And most issues are handled with simple projection, so the trainable adapters are only used when necessary. This keep memory use low while ensuring the smooth integration. And then we ensure the structure of the adapter, and then we fine-tune it only for the adapter and freezing other parameters of the assembled model. Okay, let's move on to the last challenge, the block pool itself, because the block pool is a memory based. From the table, we can see with just 5 pre-trained large language models, the FP16 version already takes up over 40 gigabytes of storage. Even if we use int8, it's still too large for many edge devices. Also, int4 helps shrink the size further, but it comes with a major trade-off. We can observe that there is a nearly 6% drop in accuracy. The existing mixed precision quantization method could help, but they are often too complex and computational expensive, especially on low-end devices. So we came up with a more practical solution, block Quanter, it is a blockwise quantization method. Here is a key idea. Since block selection is only based on the block output, we don't need to adjust the width inside the block one by one. Instead, we can apply the same precision settings across the whole block, which means all the width inside the same block will have the same precision settings. To do this, we analyze each block's width, sparsity, and output sensitivity, and then assign the higher precision to more critical blocks. This gives us a much better memory accuracy trade-off. But even after applying block Quanter, the block pool is still too big for many edge devices with limited resources. So that's why the block swiper comes in. In the block swiper, each client is assigned a memory budget, and we dynamically manage which blocks are kept in memory or in the storage. So if a needed block isn't in the memory, so we can just swipe it in from storage. To make this process more efficient, we use a smart replacement strategy that combine LRU and block correlation. So less important or less relevant blocks get swapped out first. To further reduce the I/O delays, we introduced the preloading and pre-swiping strategy based on the usage patterns. So the needed blocks are already in memory before they are requested. As shown in the figure 12, we can see compared to other block swiping pipeline strategies, our method significantly reduced latency during the process. This then allows AssyLLM to support large and diverse block pools, even on devices with very limited memory. Okay, to summary, the SAM we design four key components. The block comparator, it selects the best fitting blocks, and the elastic adapter ensures they work smoothly together. The block Quanter compresses them to fit memory budget. The block swiper further optimizes memory usage at the system level. Together, this makes SAM practical for edge devices. And this figure shows the architecture of AssyLLM. And let's move to the experiments. We use 5 popular large language models like Llama OPT, and we split them into a block pool with 28 blocks. And we test uh, the model on 3 diverse datasets, BOQ, PIC, and OBQA. For the baseline, we split the baseline into 2 groups. The first group is algorithm level. They are LoRa, QLoRa, Fed adapter, and for the LLM. The second group is the system level. We choose the recomputation and swiping strategies. All the experiment runs in a hybrid environment. For the simulation, we use the NVIDIA A100, and on actual edge devices, we use the Jetson TX2. Throughout the whole assembling process, there are 21 assembled models are generated, and the statistic is shown in the figure 13. And during the assembling process, the AssyLLM assembled 21 different models using combination from the block pool. And from the figure 14 and figure 15, we can see our method output for fine-tuning by up to 18%. And we have better performance than the PFT baselines by over 13%. We also beat BP-free method like for the LLM by around 8%. Thanks to the efficient block selection and stable training, we also see faster convergence too. We can see up to 30 times speed out over traditional method. And also, AssyLLM have better performance in the memory, energy, and communication. From this figure, we can see SLM have much lower memory and energy cost. Also, they have lower communication cost. Why? Because in each round, we only skip gradient updates, and the client just send a few bytes to each round to the server, and the they only have their blocks index and small adapters. All this makes AssyLLM ideal for the real-world edge deployments. Okay, here is a quick discussion before we close. First, how can we select these pre-trained models? Because we already know the selecting the right large language model for different downstream tasks is non-trivial. We chose diverse models, both encoder and decoder baselines, to boost generalization. But larger block pools means higher memory overhead. So in the future, we will explore smarter strategies based on the task needed and all domain alignments. Second, why does the block assembly works? Because transformer models are inherently redundant, and even if blocks are not perfectly matched, the overall model is still work. So this robustness is key to AssyLLM. And furthermore, there are still more exciting possibilities waiting to be explored, and we are just getting started. Okay, that is all from me. Thanks so much for listening. If you have any question or just want to chat about the work, feel free to email me. And I would love to hear what you think and keep exploring together. Thank you.